Our moon is shrinking and suffering from what scientists have termed moonquakes. In fact, NASA estimates that over the last several 100 million years, the moon has shrunk by about 150 feet or 50 meters. So, why exactly is the moon shrinking? And what does this shrinking mean for us? Stick around till the end of the video as we explore all of this and more. Let's go. The moon is the only place outside the Earth where mankind has set foot. The moon is the largest and brightest object in our night sky, and it stabilizes the Earth's wobble on its axis, which results in a relatively stable climate. This makes Earth a more livable planet. Additionally, it brings about tides, which produces a rhythm that has guided humans for thousands of years. Scientists believe that the moon was likely formed after a Mars-sized body collided with Earth. NASA presently operates 3 robotic spacecraft investigating the moon, including the Lunar Reconnaissance Orbiter and the twin ARTEMIS spacecraft. Not to be confused with NASA's new ARTEMIS mission to return astronauts to the moon. Whenever we look up at the moon, it does not look to be shrinking. Its size appears to be pretty constant to our eyes. However, contrary to what your eyes show you, the moon is indeed shrinking, albeit at a very slow pace. The moon wrinkles as it becomes smaller, just like a grape does when it becomes a raisin. The moon's surface crust is brittle, unlike the supple skin on a grape, so it cracks as the moon shrinks, creating thrust faults, where one area of the crust is forced up over a neighboring part. So, what exactly is causing the moon to shrink? The moon is shrinking over time because of the loss of internal heat. The moon kept a large quantity of heat when it formed over 4 billion years ago, but due to its small size, that heat gradually escapes into space. Heat causes objects to expand, and when objects release that heat into their surroundings, they begin to shrink. This is what's going on with the moon. The moon's heat dissipates with time, causing it to decrease. The more heat trapped in the moon, the faster it shrinks. So that means that the rate at which the moon is shrinking will get slower with time. Now, what are the effects of a shrinking moon? Temperature variations can result in the cracking of certain objects. For example, ice can break and crack when the temperature becomes hotter. A glass cup might also break and crack if you wash it in an environment with a very high temperature. This is because objects expand and shrink as a result of temperature changes. Similarly, the moon is literally cracking because it is shrinking from heat loss. Although the moon will never break, its shrinking causes what are called moonquakes. Because the moon's surface is brittle, shrinking unavoidably causes it to tear from time to time in a manner comparable to earthquakes. Moonquakes, however, are incredibly weak and come nowhere near the strength of even the smallest earthquakes. So, there might be no cause for alarm just yet. Thomas Waters, senior scientist in the Center for Earth and Planetary Studies at the Smithsonian National Air and Space Museum in Washington, said, "Our analysts give the first evidence that these faults are still active and likely producing moonquakes today as the moon continues to gradually cool and shrink." When viewed from the lunar surface, these fault scarps, which are typically tens of yards high and span for a few miles, resemble small, stair-step-shaped cliffs. During the Apollo 17 mission, which touched down in the Taurus-Littrow Valley in 1972, astronauts Eugene Cernan and Harrison Schmitt had to zigzag their lunar rover up and over the cliff face of the Lee-Lincoln Fault Scarp. Waters is the lead author of a study that used an algorithm, or mathematical software, created to precisely pinpoint earthquake locations identified by a sparse seismic network to evaluate data from 4 seismometers installed on the moon by the Apollo astronauts. The method provided a more accurate moonquake position estimate. Seismometers are devices that gauge the shaking caused by quakes. They track the timing and intensity of different seismic waves to estimate the epicenter's location. The study was published in Nature Geoscience on May 13, 2019. The instruments were installed on the lunar surface by astronauts during the Apollo 11, 12, 14, 15, and 16 missions. The Apollo 11 seismometer only operated for 3 weeks. but the 4 other seismometers recorded 28 shallow moonquakes from 1969 to 1977, the kind expected to be produced by these faults. On the Richter scale, the quakes ranged from about 2 to about 5. The team discovered that 8 of the 28 shallow quakes occurred within 30 kilometers of faults that could be seen on the Moon using the revised location estimations from the new algorithm. Now, it is possible to provisionally attribute the quakes to the faults since modeling by the team demonstrates that this is the distance over which substantial shaking is expected to occur, given the size of these fault scarps. In addition, the new analysis discovered that 6 of the 8 quakes occurred when the Moon was at or close to its apogee, which is the point in its orbit where it is farthest from Earth. Here, the additional tidal force from the Earth's gravity generates a peak in the overall stress, increasing the likelihood of slip events along these faults. Highly detailed images of the Moon taken by NASA's Lunar Reconnaissance Orbiter, LRO, spacecraft provide additional evidence that these faults are active. Over 3,500 fault scarps have been photographed by the Lunar Reconnaissance Orbiter camera, and some of the images show landslides or boulders at the bottom of relatively bright patches on fault scarp slopes or surrounding terrain. Weathering by solar and space radiation gradually darkens material on the lunar surface. Therefore, brighter areas represent locations that have recently been exposed to space, as would be predicted if a recent moonquake pushed material down a cliff. Examples of recent boulder fields can be seen on the VITELLO cluster's fault scarp slopes, and examples of possible bright features are connected to faults that are close to the craters Gamma Phrygia C and Mouches L. Other LROC fault images reveal tracks from boulder falls, which would be expected if the fault slipped and the ensuing quake sent boulders rolling down the cliff slopes. These tracks are proof of a recent quake because the steady rain of micrometeoroid strikes on the Moon should erase them very quickly on geological timespans. Boulder tracks along Schrödinger Basin faults have been linked to recent boulder falls caused by seismic disturbance. These findings highlight the significance of returning to the Moon. The Apollo missions helped us to know a lot of new and strange things, but they only scratched the surface. We could make significant progress in our understanding of the Moon's geology with a bigger network of sophisticated seismometers. This presents some highly potential, low-hanging fruit for science on a future mission to the Moon. And thankfully, this is what NASA intends to do with the Artemis 1 mission. The Artemis 1 moon mission will be NASA's first significant step towards returning astronauts to the surface of the Moon. Artemis 1 will be the first test flight of NASA's new Space Launch System mega rocket and the Orion crew spacecraft. The SLS rocket will launch the unmanned Orion spacecraft on a 42-day journey to orbit the Moon before returning to Earth. After 2 failed attempts, Artemis 1 is now slated to launch no earlier than mid-November, between November 12th and 27th, from Launch Complex 39B at NASA's Kennedy Space Center in Florida. NASA plans to carry out more missions to the Moon after the first Artemis mission launches. Artemis 2, scheduled for 2024, would be crewed and would orbit the Moon. And Artemis 3, scheduled for 2025, would be the first mission to land a woman and a person of color on the Moon. These missions are significant for learning more about moonquakes and the shrinking of the Moon. It also has some scientific value on its own. NASA announced 13 potential landing locations just a few weeks ago, all in the South Pole region, where water ice has been confirmed deep inside craters that never see the sun. According to Bethany Ehlman, Associate Director of the California Institute of Technology's Keck Institute for Space Studies, the sites are some of the best areas to go for lunar geology, understanding lunar ice, and studying lunar ice. He also said that the Moon is the best place to go if we really want to learn the origin of the evolution of the solar system, because the Moon has never had an atmosphere or flowing water. It is not subject to weathering and erosion, and has thus preserved evidence of its origin. The amount of detail on the Moon's surface revealed by probes such as the Lunar Reconnaissance Orbiter has been so extraordinary in the decades following the first Apollo mission that scientists have already spotted rocks on the lunar surface that they want the astronauts to collect. How we view the worlds closest to Earth has changed as a result of the discovery of moonquakes and fault lines. Although we typically think of the Moon as a lifeless, arid world, it actually has a lot going on there. Even though the moon changes slowly and moonquakes are mild, it serves as a reminder that appearances can be deceptive. The moon is a dynamic location, and it is hoped that humans will return there soon to learn more about this unique world. What do you think about the video? Let us know down in the comments section. Thanks for watching, and see you in the next one.